Alrighty, gang. Good morning. Welcome back to MAC1140 pre-calc. Today is going to be the last day where we have a kind of back and forth live lecture on exponentials and logarithms. Today we're going to pick up where we left off last time. We were talking about the kind of laws for logarithms at the very end of class last time, these algebraic properties of the log function or log functions. We're going to get a bunch of practice with that stuff today, and then we're going to start solving some equations. So, looking a little thin in here this morning. Give it a few minutes before we actually get started, so I don't want to wait too long. Now let's just go ahead and kick over the dot cam. We might as well. Okay, here we go. So this is MAC1140 section OR1. So it's pre-calc. And the date is the 10th of November, 2021. I do have a little announcement. So our exam 3, is going to be on the 17th, 1 week from today. So next Monday, so today we're going to finish the material. Next Monday, we're going to do some review, and then the test exam 3 is going to be on the 17th. It will cover exactly what you think it would. 4.1 on exponentials. 4.2 on the natural exponential and the number e. 4.3 on logarithms. 4.4 on log laws. And 4.5 on exponential and log equations. So that's it, just chapter 4, right? Exponentials and logs. Of course, as always, be aware that the test could ask you questions that have to do with concepts from previous chapters as they relate to this stuff, like we saw in section 4.3, that sometimes when you're finding the domain of a logarithm function, you need to solve an inequality. And that inequality might be a polynomial or rational inequality, depending on what's inside the logarithm. In 4.1 or 4.3, we could also ask you to do things like find average rates of change for exponential or logarithm functions. That would be a totally kosher thing. Today, we're going to be talking about log laws and exponential and log equations. Sometimes when you're solving an exponential equation or a logarithm equation, you need to do some factoring, right? So the concept from chapter 3 could be present here in those ways as well. So while these are the sections on the test, it is just the nature of mathematics that these things build. So if there's anything from those earlier tests that you're sketchy on or not comfy with, it would be wise to go back and review. In particular, if you have not done so, it would be very wise to make sure you've read the comments that I left on your written work from exams 1 and 2. Okay, with all that said, let's go ahead and start talking about some exponential equations. Or I guess we need to go over the log law stuff first. We defined those and we showed you what they are, but let's start working with them a bit. So I'm going to get the camera out of the way. We can focus just on this. I think last time we wrote down each of those three main exponent rules and looked at the corresponding logarithm rule. Like for exponentials, multiplication outside turns into addition inside. And for logarithms, the corresponding rule for that was that multiplication inside, so if you have the base A log of a product, that's the same thing as the sum outside. So the base A log of X plus the base A log of Y. And X and Y here could be anything. They could be numbers, they could be functions, they could be tables. They could be chairs, it could be people. Whatever it is, if you have a logarithm with a product inside, two things multiplied inside the logarithm, that's the same as the sum of the two logs with each individual term from the product inside. The exponential rule is a to the x over a to the y is a to the x minus y. In other words, division outside the exponential is the same as subtraction inside the exponential. And because the logarithm is the inverse to the exponential, that means division inside the base A log of x over y is going to be the same as the base A log of the top minus the base A log of the bottom. And then that third log law, I don't know if you guys watch Arrested Development, it always reminds me of Bob Loblaw's law blog. The third log law is that the base A log of a power, x to the y, is the same as y times the base A log of x. So exponentials, remember, a to the x all to the y is a to the x times y. So powers outside become multiples inside. And here for logarithms, it's kind of the exact opposite. Powers inside become multiples outside. So each one of these corresponds really nicely to an exponent rule. Again, x and y here can be anything. They could be expressions, they could be functions, they could be numbers, or they could just be an individual variable. When you use one of these rules, you need to make sure you're using it exactly. I'll say one that's often kind of misused is this guy. I'll point out the common mistake when it shows up here. But there are several ways to misinterpret each of these things, and you want to make sure that you're using them precisely as they're stated. Also, each of these can be used in two directions. If I give you a log of a product, you can expand that into a sum of logs. Or if I give you a sum of logs, you can combine that into a single log with a product inside. So let's look at a couple examples. You need to remember these. These need to be burned into your brain forever and ever, amen. Just like the rules for exponents need to be burned into your brain forever and ever, amen. So let's use log laws to help in evaluating the following expressions. The base 4 log of 2 plus the base 4 log of 32. And the base 2 log of 80 minus the base 2 log of 5. This last one from this part of the textbook, I'm not crazy about because it will require a calculator at the end, whereas the other ones do not. But negative 1/3 times the log of 8. And remember, log without a base written here is always the base 10 logarithm. All right. So if you look at part A, this is kind of the tamest of all of these. We actually can figure out the base 4 log of 2. All right, that's not terribly hard. 4 to what power is 2? Well, the square root of 4 is 2, so 4 to the 1/2 is 2. So this guy should be 1/2. We could apply similar logic to find the base 4 log of 32. Although it's not quite as clear, I think this is going to come up to something like 5/2. But I don't think either of those are super obvious. And kind of the point here is to use these laws of logarithms to rewrite each expression in a way that makes it easier to evaluate. So does anybody see one of the log laws that we could apply to the expression in part A? Which one of those 3 rules we just wrote down applies here? You just tell me 1, 2, or 3. The first rule, second rule, or third rule.
The first rule.
Yeah, definitely the first rule, right? This is a sum of 2 logarithms, right? This is 1 log with base 4 plus some other log with base 4. So because I'm adding up 2 logs of the same base, that is the same as a single base 4 logarithm. Ooh, this purple's no good. Single base 4 logarithm with their product inside. So what would go inside here would be 2 times 32. All right, addition outside is the same as multiplication inside. 2 times 32 is 64. And this is easier to sort out. What is the base 4 log of 64? Yeah, 3. I heard it from Eric there. So remember, the question you need to ask yourself when you're trying to compute something like this is, to what power must I raise this base 4 in order to get this inside 64? So 4 to the 1 is 4. 4 squared is 16. 4 cubed is 64. So the base 4 log of 64 is 3, because 4 to the 3 is 64. This next one's a little gnarlier when we start, because the base 2 log of 80 is not a nice power of 2, not even a rational power of 2. And the same is true of 5, right? 5 is not any rational power of 2. But if I combine these using one of my log laws, I would get the log base 2 of, well, let's see, I'm doing subtraction outside. That means we're going to do division inside. And what goes inside is this over this. So that's the base 2 log of 80 over 5. And 5 goes into 80 16 times. So this is the base 2 log of 16. How do we find the base 2 log of 16? What is that?
Four, isn't it?
It is, yeah. 2 to the 4 is 16. So the base 2 log of 16 is 4. If you're not yet comfortable with these things, I'll warn you, the test will have problems that not only require you to answer these questions, but to explain your reasoning. So you do need to take the time to work through that first logarithm homework in earnest. All right, this next guy, I'm not a huge fan of, because like I said, there's no way of avoiding some calculator usage here. So I'm going to go ahead and launch. I couldn't find a TI-30 emulator. I was a little disappointed that we didn't have access to a TI-30 emulator through the Santa Fe kind of software package we get, but I do have an 84 emulator called Wabbit. So I'll show you how we're going to clean this up and then how you would enter that into a calculator. First, I have that rule which says powers outside are multiples outside are the same as powers inside. So I can bring that negative 1/3 in. And this will become the log of 8 to the negative 1/3 power. Eight to the negative 1/3 is 1 over the cube root of 8. The cube root of 8 is 2. So this is the log of 1/2. Now, remember, log without a base written always means base 10. That's the common logarithm. Certainly, it's not true that 1/2 is a nice power of 10. There is no integer or even rational number to which you can raise 10 and get 1/2 out. But if you look on your calculator, just like this 84 here, you will have two buttons related to logarithms. One will say log, the other one will say ln. The log is the base 10 or common log, and the ln is the base e or natural log. So here I would type log 1 divided by 2 and close that parentheses, use good syntax. And we get negative 0.30102, blah, blah, blah. So it's like negative 0.301. Rounding up the third decimal there. On your test, there will be problems that explicitly say do this without a calculator, and these two could be examples of that. So I could say combine these into a single log, evaluate that log, and explain why. Questions on any of these? Okay. One of the other things that we often do, one of the other things that will certainly show up on your test, is asking you to take an expression with variables and either expand the logarithm or combine into a single log. We're going to start by expanding. So I'll say expand each log expression as much as possible. And I'm going to, if you're following along in the book, I'm going to add one more here because I feel like this is a little sparse. So these are the expressions we're going to expand. The first one is fairly straightforward. There's only one thing going on inside that logarithm. If we look here, this is the base 2 log of 6x, and 6x is 6 times x. So this is a log with some multiplication going on inside. So according to that first rule, I can expand this as the sum of two logarithms. First one being the base 2 log of 6, second one being the base 2 log of x. There are ways of thinking about this, by the way, as a transformation. Remember, multiplying by a constant on the inside is a horizontal scaling. Adding a constant, this is just a constant on the outside, is a vertical shift. So for some logarithms, a horizontal scaling is the same as a vertical shift. In fact, for all logarithms, a horizontal scaling can always be reinterpreted as a vertical shift. I think that's kind of cool. looking at the second guy here, there's sort of two things going on, right? I've got some multiplication inside the log, and then I've also got powers inside the log. And I'd like to ask you, which one should I handle first? Should I try to bring the powers down first, right, using that third rule? Or should I try to take this multiplication and split it up into addition outside first?
Wouldn't you split it up since we're dealing with an X and a Y?
Yeah, I like Drew's answer there. Definitely first we need to split it up. That we have two different variables here is one way of sort of thinking about it. The other thing here, which power would I bring down? If I wanted to bring the powers down first, rather than splitting it up, do I bring down the 3? Is this the same as 3 times the base 5 log of x times y to the 6? Or do I bring down the 6? Is this the same as 6 times the base 5 log of x cubed y? And the answer to both of those questions I just asked is no. Only the x is being raised to the 3, and only the y is being raised to the 6. And I think that's what Drew means there, because we've got these two different variables. So when you're bringing powers down using that third logarithm rule, it needs to be the case that everything inside that logarithm is raised to that power, right? Because having, for example, a 6 out front here would mean everything inside is raised to the 6. Oh, but that's not true, right? The x is only raised to the 3. So first we need to split it up. This would split up as the base 5 log of x cubed plus the base 5 log of y to the 6. And now each of those, the whole inside of this logarithm is being raised to the third power. So I can bring the 3 down, but only in front of this guy. And here, the whole inside of this logarithm is being raised to the 6. So I can bring the 6 down, but it's only attached to this guy. So this would be 3 times the base 5 log of x plus 6 times the base 5 log of y. And you see that is not the same thing we would get if we tried to bring either or both of these powers down first and then split up. So kind of only the x had the cube, so only the x term here should have a 3. Only the y had the 6, so only the y term here should have the 6. I think these next two I'll move on to a separate piece of paper because each of them is going to take a little bit more space. So I'm just going to rewrite this, the natural log of a times b over the cube root of c equals. Following the same sort of idea that we did here, where we split up the multiplication before dealing with the powers, what you want to look for here, or in any of these problems when they get a little bit more complex like this, is kind of what is the outermost operation going on inside the logarithm. So I've got some multiplication up here, right? A times b. I've got a power down here. That cube root, remember, is the 1/3 power. And I'm dividing those things. AB is being divided by cube root of c, or c to the 1/3. You want to split up or expand starting with the outermost operation. Now, if you're actually very careful with your order of operations, you realize that kind of doesn't matter, but you have to be extremely careful if you're going to mess with this in any other way. So visually, when I look at this, just from the notation, what appears to be the outermost operation is this division. All right, I've got a big fraction inside. The top has some multiplication, the bottom has a power, but the outermost operation appears to be this division. So this would be the natural log of AB minus the natural log of the cube root of c. subtracted. That's that second rule. Now, each of these guys, we can do something with. In my next step, I would expand the natural log of AB as the natural log of A plus the natural log of B. All right, multiplication inside is addition outside. And maybe here I'll just write this as the ln of c to the 1/3. Don't try to do too much at once. I've seen people who know these rules and have good algebra skills make mistakes and lose points on tests and stuff like that by trying to do too much at once. So if there's one thing I can impart to you, especially if you're feeling comfy and confident, it's to take your time and do one, at most two things at a given step. Don't try to do it all at once. The final move here would be to manage this 1/3 power inside. All right, the ln of c to the 1/3, everything else staying the same. The ln of c to the 1/3 is 1/3 times the ln of c. And a neat trick, if you're looking at your expanded version and wondering, is this correct? One worthwhile check is to ask, did all the terms from upstairs end up positive and all the terms from downstairs end up negative? Right? Everything that's downstairs inside the log should end up with a negative term when you expand that log. And the next example, part D, is a good place to show one way we can make mistakes there. But that little mental check is a good one. So if a term was downstairs inside the log, the corresponding term in the expanded version should be negative. And if a term was upstairs inside the log, its term should be positive in the expanded version. All right, part B, I'll just rewrite it here, asked us to expand the ln of x squared over y times the square root of z. So again, sort of the outermost thing I see going on in here is this division. So I'll begin by writing this as the ln of the top minus the ln of the bottom. Looking at that first term, the ln of x squared is the same by our third rule as 2 times the ln of x. And then I have minus, I'll just leave this alone for now. Maybe I'll write that z as square root z as z to the 1/2. I can't bring this 1/2 out yet because the y here is not raised to the 1/2 power. All right, so in order to bring a power down, everything inside the log needs to be raised to that power. You have to have like parentheses, all that shit to the power, which is not what we have here. So the 1/2 can't come out at this step. What I can do with this piece, because it has some multiplication inside, is rewrite it as a sum of two other logarithms. The ln of y times z to the 1/2 is the ln of y plus the ln of z to the 1/2. And I'm going to write this down, and then we're going to look at it carefully. Is this correct?
Do you have to expand the negative?
Everybody hear what Shauna said? Thinking about what we said here, that little mental check, every term that comes from the downstairs inside should be negative in the expanded version. Well, if I write this like this term appears to be positive, doesn't it? Now, covering up everything else, this is true. The ln of y times root z is the ln of y times z to the 1/2 is the ln of y plus the ln of z to the 1/2. But this guy is negative. This guy is negative, which means this whole thing should be negative, which means we need parentheses. Anytime you're replacing a single term, this is a single term, technically, the ln of some shit, whatever that shit is, that's one term. Anytime you're replacing a single term by an equivalent sum of two terms or more, you need to put it in parentheses. This was a chunk, and I need to treat it as a chunk. And that whole chunk was being subtracted. So that whole chunk in parentheses needs to be subtracted. And that little mental check, did this term come from downstairs? Yeah, it did. That was the square root of z downstairs. Okay, so I know he needs to be negative in the expanded version. So distributing that negative and pulling down the 1/2, we get this. This is not correct. Right? But without the parentheses, the previous line is not correct. And if you were to jump from this line without parens to this line, I would still have to take off like a half point or something. So we really need these parentheses. When you're expanding terms that come from the downstairs inside a logarithm, please put it in parentheses. It's important. Right, without these parentheses, this line is not equal to this line. Are y'all comfy with that? I appreciate the good catch there, Shauna. You'd be surprised how rarely anybody notices that. So nicely done. All right. So expanding logarithms, not that bad. All right. Just at the very least, make sure the signs are correct when you're done. Most of it is fairly intuitive, and I don't find that people usually have a terribly hard time with this as long as we're keeping things reasonably simple inside. Hard versions of problems like these, the log of a polynomial, and then you factor the polynomial inside and expand. Or the log of a rational function, and you factor top and bottom inside and then expand. I used to put those on tests in this class, but then I started getting worried that someone was going to stalk me and kill me in the parking lot, so I stopped. But just be aware, that sort of stuff exists, and you will see it in Calc 1. Right? One of the reasons we talk so much about these things in pre-calculus is because there's a technique in Calculus 1 called logarithmic differentiation. That's where you want to do a calculus operation to a big fraction, a big rational function or something like that. The calculus operations on those things, unpleasant, very unpleasant. But the calculus operation on logarithms of single terms, very nice. So instead of doing the calculus operation on the original big nasty fraction, you take the logarithm of that fraction and then expand it out and do the calculus operation on something like this. Oftentimes that requires you factoring top and bottom inside, but most of the problems I could give you in this class wouldn't require you to do that. So making sure you understand these examples, the problems in the homework, you'll be good on the test. Okay. You can imagine instead of giving you this and saying expand, I could give you this and say combine. Indeed, that's a thing. So let's take a look at one or two problems like that. All right, so I'm going to give you a couple of expressions here that we want to combine into a single logarithm. Something like 3 times the common log of x plus 1/2 times the common log of x plus 1, or 3 times the natural log of z plus 1/2 times the natural log of t, minus 4 times the natural log of t squared plus 1. We want to run those same steps that we were doing in the previous problem, but backwards. And we want to run the steps in reverse order. So if this was coming from some expanded log, the last thing we would have done is pull down the powers, right? If you look at those last few problems, the very final step in each of those was pulling down the powers and bringing them out front as multiples. So if I want to undo that procedure, I need to take these multiples and bring them inside as powers. And you need to be a little bit careful when you have stuff like this, where you've got multiple terms inside the logarithm. Make sure that everybody gets that power in the appropriate form. So the first one is easy. This is the log of x to the 3, just bringing that 3 inside as a power. Plus, the second one is going to be the log of, and you're going to need to stack up some parentheses here. It's not just the x that's getting raised to the 1/2. It's not just the 1 that's getting raised to the 1/2. And it's not those two things separately getting raised to the 1/2. It's the whole thing, x plus 1 as a chunk that's getting raised to the 1/2. So this would be paren x plus 1 to the 1/2 like this. Now we can combine. The sum of logs is the log of the product. So that's the log of x cubed times, I'll write this as a square root, times x plus 1 to the 1/2, or the square root of x plus 1. Second guy is more of the same. So I begin here by saying, okay, this is the ln of z cubed plus the ln of t to the 1/2 minus the ln of paren t squared plus 1 to the 4. And remember, taking something like t squared plus 1 and raising it all to the 4 is not the same as raising t squared to the 4 and 1 to the 4 separately. Right? So there really is no nicer way to write this. Then again, remembering to not do too much at once, let's combine the first two pieces. This gives me the ln of z cubed times t to the 1/2 is the square root of t minus the ln of t squared plus 1 to the 4. Having this addition outside to multiplication inside, and then finally, you can write that as a single log with z cubed root t upstairs and t squared plus 1 to the 4 downstairs. Okay. So one of the very common mistakes we've already addressed, expanding logarithms, making sure you distribute the negative to any pieces that come from the denominator. That's important. There are a couple other ways that people often conflate or make mistakes with these log laws. And I just want to point out one or two of them. First, let's look at this piece right here, just this piece. The log of x plus 1 to the 1/2 like this. I said you have to stack up those parentheses. And that's for a good reason, because this is not the same as the log of x plus 1 to the 1/2 like this. Remember, we talked about the ambiguity issues that can come up if you don't put the inside of the log in parens. If you write this, people will think you're talking about this. which is the square root of the log of x plus 1. All right, so the power being kind of inside the log here is different than having the power outside the log. And that's one of the reasons we always write these parentheses. So here's the log. This is the parentheses that tells you what's inside the log. What's inside the log? It's x plus 1 to the 1/2. Without those parentheses, it looks like you're taking the whole expression log of x plus 1 and raising that to the 1/2. Those are not the same. Another similar mistake. If you have something like the log base 2 of x all cubed, this is not 3 times the log base 2 of x. Because again, same sort of thing here, the power is on the outside of the logarithm, not inside. This would be log base 2 of x cubed, like this. And those are very different animals. The good news is you're not actually going to encounter things like this a whole lot. And those of you taking trigonometry, there are nice ways to describe powers of logarithms using the same sort of notation, like you write sine squared or sine cubed. A lot of people write log squared or log cubed, putting the power right here instead of like on the outside. But again, you're not going to encounter that sort of stuff very often. It's just an important notation comment. Make sure you're clear on what you're writing. All right, these next two are really killers. These next two are things I see all the time. For any base A and any numbers x and y, which are positive, it is not true that the base A log of x plus y is the base A log of x plus the base A log of y. This shit never works. Never, ever, ever works. I mentioned this the other day. This is not multiplication. This is not the base A log times x plus y. This is a function. This is the base A log of x plus y. Think of this base A log as being like f. This is like f of x plus y. And for the same reason, like when we talked about difference quotients way back at the start of the semester, you can't distribute the f. You can't distribute the log. It's not multiplication, it's function notation. This is the name of the function we are playing with, and this is the thing that we are plugging into the function called log base A. And there is no rule for logarithms that has anything to do with addition inside. And if you go back and look at those log rules, none of them have x plus y inside. There is a rule for stuff like this. What this is actually equal to is the base A log of x times y. So addition outside is multiplication inside, but addition inside ain't nothing. And in particular, it ain't the log of x plus the log of y. So you cannot ever distribute logarithms like that. Doesn't work. So I see this all the time. Every time I give the test that comes up, somebody does this. Please don't do that. The other one that's like this, something like this, is not the same as something like this. Right, so one log with division inside is not the same as dividing the logs. This shit never works. So please just be very careful, right? I see these two a lot. Common mistakes. And I understand why we want to do that, right? It feels kind of like a natural thing to do just based on the notation. But this shit literally never works. So we need to be very careful. The moral of the story here is when you're manipulating logarithm expressions, make sure you use those log rules and just those log rules, nothing else, right? Nothing besides the things that we tell you work. Okay. So with that said, there are occasions where you'll bump into expressions like these. And I think I would like to introduce those rather than right here by talking about the start of the next section, which is exponential and logarithm equations. So while there's one more little property or formula associated with logarithms, I think it is nice to introduce it as a consequence of some of the others. So this is the last section that's on the test. It's section 4.5.
You say this is the last section?
Yes. Yeah, this is the last section that is on exam 3, section 4.5. An exponential equation, remember we started everything all this log stuff. I think we mentioned this the other day. All this log stuff started with the equation two to the x equals 3. And we can solve this now. The trick for solving equations like this is a new operation. And I hinted at it a moment ago, taking logarithms on both sides. So an equation like this is called an exponential equation because the variable is up in the exponent, right? This is an exponential function. So an equation involving an exponential function is called an exponential equation. The way we do it is by applying this new operation called take logs. And it's up to you what base logarithm you want to take, right? There are many different logs. You could use the base 7 logarithm. You could use the natural logarithm. You could use the base 2 logarithm. I'm going to solve this equation 2 different ways. First, I'm going to solve it by taking the base 2 logarithm on both sides. What that means is I'm going to put both sides of this equation inside the base 2 log. We're allowed to do this because the logarithm is a one-to-one function. So if these things are equal, these things must be equal. And if these things are equal, these things must be equal. Hence the if and only if symbol here. Think of it like taking square roots on both sides. Same sort of thing, right? You put both sides of the equation into a square root. Or cubing both sides. You put both sides into the third power. Here we are putting both sides into the logarithm, so we call it taking logs. The right-hand side of this equation, there's not really anything else I can do. But the left-hand side of this equation simplifies very nicely. What is the base 2 log of 2 to the x? Think back to, I think we mentioned it in the previous lecture, but focus mostly on this the lecture before.
X.
Yeah, it's just x, right? The base a log of a to some stuff is always just that stuff. So the base 2 log of 2 to the x, that's just x. So this says x equals the base 2 logarithm of 3. And this is that number that I wrote down for you. This is that 1.54896, blah, blah, blah. We would refer to this as the approximate solution. This is the decimal approximation. And this is the exact solution. There is a downside to what I've done here. This answer, the base 2 log of 3, is not something I have a button for on my calculator. Now, it is true that on the TI 80 series, I think somewhere in here, you do have a log base function. But again, you guys are working in the TI 30, which I don't believe has that function. So if I wanted to take this and get this decimal, it's not immediately obvious how I do that using a kind of simple calculator. Another way to solve this I could have used any other logarithm I wanted. There's nothing sacred about the base 2 logarithm. In fact, all logarithms are essentially the same. What is true is that the base 2 logarithm is the one that's super duper nice here, right? The base 2 log of 2 to the x is going to simplify to x. And if I use some other logarithm besides the base 2, it wouldn't clean up quite that nicely right away. But watch what happens when I take the natural log. So again, the first step here is to take logs. That's one of 2 new operations we're going to learn in this section. And this time I will take the ln of both sides, giving me the ln of 2 to the x equals the ln of 3. And it's true, the left-hand side is not quite as pretty here, right? The ln of 2 to the x is not x. But based on the rules we just learned, what can I do with this x? So don't worry about the right-hand side. Look at just the left-hand side. What can I do with the power inside this logarithm? I think Eric was about to say something.
Yeah, isn't that the one where you take it out and put it behind it?
Yeah, right. So the log of something raised to a power, that power can come down. So this is the same as, right? Powers inside are multiples outside. That means this is the same as x times the natural log of 2 equals the natural log of 3. And I don't want you to be intimidated by this. I had a funny moment with one of my Calc 2 classes where we used an infinite series to approximate this number to a high degree of precision. The first few digits of the natural log of 2, this is just a number, are 0.69. And I know that those 2 digits stick into people's head well. So this is just a number. Don't be afraid of it. The ln of 2 is approximately 0.69. And for whatever reason, my Calc 2 students thought it was very funny to just say nice. All right, but the take home here, just a number. Don't be afraid of it. It's like 5 or 10 or pi. This is just like x times some number equals some other number. So if I want to solve this equation now, all I have to do is divide over by that number that is multiplying x. This means x is the ln of 3 divided by the ln of 2. And this has an interesting consequence. See here, I have two exact solutions to the same equation. We can plug the second one into my calculator, though. You can plug the second one into your calculator, the ln of 3 over the ln of 2. ln 3, close paren. Careful with your parentheses, right? Got to close that paren. Divided by ln of 2, close paren. And you get that same number, 1.58496. Oh, did I transpose the 8 and the 4? No. 1.5. 496, 1.58496. So this and this are the same number, which means this and this are the same number. A few comments here. I'm going to solve more exponential equations for you today because this is the section we're in now. And when I do that, I'm always going to use the natural log, right? The natural log, in the same way that everybody likes e to the x and will go through great lengths to avoid using other exponentials, the natural log is everybody's favorite logarithm, and I will go through great lengths to avoid using other base logarithms. Multiple reasons. If you like, one of them is that you have a natural log button on your calculator. You don't have a base 2 log button on your calculator. So when I take logs on both sides of an exponential equation, I'm going to take the natural log. You could use other logs, and those will sometimes clean up a little faster. But if you need to figure out what this number is, it turns out the only nice way to get this decimal approximation, you want to know what I was doing the other day when I first gave you that number, I had a calculator that I punched ln3 over ln2 into. The first time I wrote this number down for you, that's how I calculated it. So rather than going through the process of taking the base 2 log, writing this, and then through a certain formula saying the base 2 log of 3 is the same as the ln of 3 over the ln of 2, just do this. Just do this. This is better, right? This procedure is the one that works for everything and is calculatable using common technologies. So what's the result here that I'm hinting at? Well, base 2 log of 3 is 1.58496. ln3 over ln2 is 1.58496. So if you change the 3 and the 2 here to something else, you could change the 3 and the 2 here to something else. This is called the change of base formula. So this illustrates and that change of base formula can be written in a very general way, and then I'm going to give you a specific instance of it that is the way we really use it. What I mean when I say it's more general, what we've done here is we turned a base 2 logarithm into a natural logarithm, right? I had a base 2 log that I was able to rewrite as a natural log, a ratio of natural logs. In general, given a base b logarithm, the base b log of x, if you want to change this into a base c logarithm, the way you do that is by taking the base c log of x and dividing it by the base c log of b. So if you want to change some weird base logarithm into some nice base logarithm, if c is a nice base for you, then you can take your weird base logarithm and write it as the nice base of the inside divided by the nice base of the old base. And there are two special cases. If you take c to be 10, then this says that any weird base log of x is the same as the common log of x divided by the common log of the old base. Or if you take c to be e, you can take any weird base log of x and write it as the ln of x divided by the ln of b. And it's that last one's the way we usually do it. So if you're given some funky base logarithm that you need to compute, it's the natural log of the inside over the natural log of the base. That's the way to do it. Now, in practice, as we solve equations, you just leave your exact solutions like this, right? This is the nicest way to write that exact solution, because it's easy to punch into a calculator and get a feel for how big that number is. All right, let's look at some equations. Look at some more equations. I could ask you to solve three to the x plus 1 equals 7. Seven is not a nice power of 3. There's no way to sort of just mentally reason your way there. So what we're going to do is take logarithms. I'm going to take the natural log on both sides. So I have the natural log of 3 to the x plus 1 equals the natural log of 7. Then I use my properties of logarithms to bring this power down in front. And just like when we saw in these other cases, you're using these rules to bring a piece down that has 2 terms. You need to do that with parentheses. This is parentheses x plus 1 times the ln of 3 equals the ln of 7. Right? The power here inside was x plus 1, so that comes down. If I want to get x alone, I can divide both sides by the natural log of 3, giving me x plus 1 equals ln of 7 over the ln of 3, which means that x itself is ln 7 over ln 3 minus 1. And then if I want a decimal approximation, you can compute the natural log of 7 over the natural log of 3 and then subtract 1 from that. Be careful with your order of operations. You notice I computed that ratio and then subtracted 1 just to be careful. I recommend that you enter these in ways that you're 100% confident you're doing it correctly. So this comes out to about 0.7712. And again, this would be your exact answer. This would be your decimal approximation. And the problems in the homework I'm going to open up for you today ask for both. Or sometimes they just ask for one. We need to know how to give both. On the test, I'll most likely tell you to just leave your answers in the exact form. There might be a problem or two where I ask for a decimal. Questions on this guy? Okay, let's look at one more. I could ask you to solve something like 8e to the 2x equals 10. Before we take logarithms, I want to get this into the form like exponential equals constant. So this 8 is kind of in the way. So I would begin here by dividing both sides by 8. So this e to the 2x equals 10 over 8. I can simplify 10 over 8. They're both divisible by 2. So this is 5 over 4. Nice to do that. And then I can take logs. So the ln of e to the 2x on the left and the ln of 5 over 4 on the right. Again, I'll always use the natural log. There's no reason to use any other log. Here, using the natural log is ultra nice. What is the ln of e to the 2x? Yeah, it's just 2x, right? The ln, that's the base e logarithm. So we don't have to do the same sort of thing that we did here, where we bring the power down and have something else left over. The ln of e to some stuff will always just be that stuff. So this is just 2x equals the ln of 5/4. And then we can divide both sides by 2. So this is x equals the ln of 5/4 all over 2. If you want, you could write this as 1/2 times the ln of 5/4, but you don't have to. Either one is fine. And your decimal approximation here. And making sure you close this parentheses before dividing by 2 is very important. Is 0.11157. Oh. Questions on the second guy? I want to outline the procedure here for solving exponential equations. Like we saw here, the first thing you need to do is isolate the exponential. All right, I had to get rid of the 8 first. If you try to jump in and take logs here before getting rid of the 8, you need to be extremely careful how you handle the ln of 8 times e to the 2x. It can be done, but it gets messy. So much smarter to isolate the exponential first. Then you will take logs. And generally, and take the ln of both sides. And you're going to bring down the power. And then you're going to solve the resulting equation. The miracle here is that when you take the log on both sides, your exponential equation turns into a linear equation, or at least no longer is exponential, right? This is a linear equation. The x here is just upstairs to the power of 1 multiplied by some constant. This is a linear equation. It looks a little weird because this number over here is a weird number, but it really is linear. Again, the place where people maybe make mistakes here is not isolating the exponential and then messing up how to handle the ln of this because of the 8. So isolate the exponential first. The majority of the equations you're going to see look something like this. You know, maybe there's a +1 over here or something like that that you need to get rid of before you take logs. There are a few types of equations you'll run into that are perhaps a little trickier than that. And in the last few minutes here, I just want to show you some examples of those where it's not ultra straightforward in the way that those first ones were. One of my favorite examples here, we look at e to the 2x minus e to the x minus 6 equals 0. Certainly an exponential equation. All right, my variable is up here in the exponent. It's here in 2 terms. So there's no easy way to isolate the exponential here. It can be done, but it's not going to be like add the 6 over or anything like that. That's not going to work. In fact, this is secretly a quadratic equation. The idea is that e to the 2 times x is e to the x all to the 2. So this is e to the x squared minus e to the x minus 6 equals 0. And this is quadratic in the variable, I'll say u equals e to the x. In other words, you're going to make a little substitution, and then you're going to factor. Some people like to factor from here. If you see that, that's great. But I think a lot of people are a bit intimidated trying to factor something like this, even though it is secretly a quadratic. If you want to see it as a quadratic better, make this substitution. Because then you get u squared minus u minus 6 equals 0. And this is not hard to factor. This is u minus 3 times u plus 2.
Can I ask a question really quick?
Sure.
How did you get e to the x is squared from e of 2 to the x?
So the algebra rule that we're using there is one of those rules for exponents. Remember, a to the x times y is the same as a to the x all to the y. This was one of those rules for exponents we talked about at the start of chapter 4. I think we wrote it with this on the left and this on the right.
Okay, thank you.
Yeah, no worries. But yeah, e to the 2 times x is the same as e to the x all to the 2 by this rule. And it is sneaky. It is sneaky. From here, of course, I would set each factor to 0, just like you would with any other quadratic. So this guy would tell me, setting him equal to 0, that u is equal to 3. And this guy would tell me that u is equal to negative 2, which means e to the x is equal to 3, or e to the x is equal to negative 2. One of these gives a solution. One of them does not. Which one does not give us a solution? Take a quick look at the graph of e to the x. Here's y equals e to the x. It's got a horizontal asymptote, y equals 0, goes to 0, 1, all that good stuff. Does this graph ever intersect the graph y equals -2?
Nope.
Hell no. -2 is like down here, right? So this thing never touches that. There's this guy has no solution. And the way people usually like to say this is because e to the x, this curve, is always above the x-axis. E to the x is always strictly positive. Right? E to the x could never be equal to -2 because e to the x is always bigger than 0. The other guy does give me a solution. If I take the natural log on both sides, the natural log of e to the x equals the natural log of 3. So x is ln 3, and this is your only solution. I know we have gone just a couple minutes over at this point. There's one more equation I want to look at with you guys before I let you go. So I'm going to ask you to hang on for just 10 more seconds. I promise this next one will be fast. But you will see things like this from time to time. You will see things like this from time to time. If you have an equation where you've just got e to the 2x and e to the x showing up in separate terms, try rewriting e to the 2x as e to the x all squared and substituting u equals e to the x. If you're lucky, that'll give you a polynomial, which you can factor and then plug back in for u and try to solve. Just be mindful that e to the x will never be 0 and will never be negative. E to the x is always strictly positive. All right, last one. How about 3x times e to the x plus x squared times e to the x equals 0. I've got a bunch of stuff on the left-hand side and the right-hand side is 0. So kind of in the same way that we wanted to factor in the last one, I want to factor here. There's a common factor of x that I can pull out. In fact, let me pull out the e to the x first. So this is 3x plus x squared all times e to the x equals 0. So I can factor out an e to the x, and what's left is 3x plus x squared. And then in the 3x plus x squared, I can factor out an x. I get x times 3 plus x times e to the x equals 0. And now this is fully factored. I've got something times something else is all equal to 0. That means either x is 0 or 3 plus x is 0 or e to the x is 0. Well, x equals 0, that's done. Nothing more to do there. 3 plus x equals 0. I can subtract 3 from both sides. I get x equals -3. So these guys are definitely two solutions to this equation. Does this guy yield any solutions? Is e to the x ever equal to 0?
Nope.
Nope. Again, no solution because e to the x is always strictly positive. Okay, so this is kind of the first half of section 4.5, and the homework I'm going to release for you right now is 4.4 and 4.5 part 1. I'm going to record a video lecture for you that will cover the second half of section 4.5, because I don't want to wait until next Monday to show you that and then have you take the test on Wednesday. That feels a little bit rushed. But also with Thanksgiving and everything, all the holidays coming up, we can't afford to lose a bunch of time here. So I am going to record a video lecture for you that covers the second part of section 4.5, and then I will release a homework for that like tomorrow. Watch that video lecture over the weekend or as soon as you comfortably can, and then work on all of those homeworks, the 4.4 and 4.5 part 1 and the 4.5 part 2 homework at your leisure between today and Monday of next week. Remember, Wednesday of next week is your test. So in addition to those homeworks, I'll also be releasing a quiz that you can kind of use as a review for the test. I don't want to overwhelm you, so the quiz and these homeworks will be somewhat short, or as short as I can make them without making them inappropriately short. If you're stuck on anything, you can always come by office hours, send me a Canvas message, post on Discord. You all know the drill at this point. That's it for me. I'll see you guys next time.